Hi, my name is Mark Lancaster, and I'm with Permian Production Equipment. And we're going to go over a project, a new system that we've had out for the last couple of years for multi-phase compression. And multi-phase compression is basically where you can move gas and fluid in the same stroke. This is our system. Get through history of it. Now, nobody in this room, well, one person in this room is probably old enough to remember when this TV show was out. And when I was growing up, this is how you made an oil well. You stuck a hole in the ground, and oil came out, and it came up for only one reason, and that was because of pressure. Everything that you've seen in the past 2 days is all regard to pressure. It's either the lack of it or too much. That's what we're working on in the oil business. Either you have too much pressure or not enough pressure. And how do you get back to the other way? Now here's a guy, and he's getting rid of gas pressure by venting it, which is pretty cool. He knows he's got too much pressure in the well, so he's going to blow it down, and he's trying to do it in a fairly safe way. And that's good. But a lot of times the well decides it's going to relieve its pressure on its own schedule. And something like this happens. Which is a bad thing, but it's not nearly as bad when it does that and some spark happens. And then you got a really bad thing. But all of this is caused by pressure. So we're trying to make oil wells, and we're trying to increase production, and we're trying to do stuff. Now I added some slides in here in case my video didn't work on LinkedIn, so you have to beg me. I think that's just funny. I haven't got sued yet. Copyright from Judd Clampett, but I don't. Some back history: the beam gas compressor was created by my boss 40 years ago in the Sandhills of Monahans. He was out with a Gulf oil engineer, and they were looking at doing some plunger lift installations. And this 40 years ago, when they did a plunger lift, it was on a well. Usually they made 5 or 6 barrels of oil or something. And they had just walked by this well where the pumper had blown it down, because if he didn't get rid of the pressure in the casing, the well wouldn't pump, because you wouldn't ever gain fluid. So he set it to blow it down. But what he did, unlike the first guy where he just had the pipe sticking here, he had the pipe going through sand dunes so it would blow out way over there, because there was H2S gas in it. Well, they didn't really notice that until they had drove up on it, and as they drove up, they saw there was a covey of quail dead on the ground, because unfortunately the quail happened to be going this way when the gas came out of the sand and killed them. And at that time, back in the 80s, there was a shortage of pumping units. There was an oil rush, and people were drilling more oil wells, but at that time, Lufkin was probably the only game in town where you could buy a pumping unit. So if you had a 640 pumping unit on a well making 5 or 6 barrels of oil, and you just drilled a vertical well making 60 barrels of oil, but you couldn't buy a pumping unit, you were screwed. So what he developed was that he could take a cylinder and set it on top of the rod string, and then you could stroke that rod string pneumatically. And so for that 3 or 4 barrels that you're trying to get out, you could stroke it pneumatically, and then you take that pumping unit now and you can put it over this other well. And if you ever go to the Petroleum Museum in Midland and you go out in the boneyards they have out back, you can see one of his machines that are out there. It's just a big cylinder. So they'd already been in the process of cylinders, and he looked at this pumping unit and he goes, that pumping unit is probably one of the most efficient pieces of equipment ever known to man, other than a 36-inch pipe wrench. Because it just works, just goes up and down. So if he took his cylinder that he'd been using for wells and inside the structure of the pumping unit, now he could use the energy of the pumping unit to pull the piston rod up and down to be able to relieve the back pressure on that well, to eliminate somebody from venting the well in order to get rid of gas interference. And so that was where the beam gas compressor came up, and he spent time over in Lufkin, Texas, and the Lufkin guys at that time were knife guys, and they helped in looking at doing all of this work. So what we've gone and done is that, we can take a well that, in this instance, you see that the gas bubbles are going up the pump. And that's pretty typical whenever you have a well that has gas interference. And gas interference is really because the casing pressure in the annulus is such an amount that the gas would just as soon go up the pump every time the plunger goes up as it would go up the annulus. Because gas is not particular, it'll go wherever it has a path of least resistance. So this is what you see normally in most vertical wells. You have some kind of a Mother Hubbard gas separator below the pump, casing pressure, fluid, that all makes up your bottom hole pressure. And so when people are trying to increase oil production, and Lance has tried this a couple times on his wells, we haven't yet been successful. Because typically if you're trying to lower your bottom hole pressure, you want to get rid of casing pressure. That's the simplest thing to do. And once you take casing pressure off, the gas bubbles will rise faster and get out of the casing. So here we go, we install a beam gas compressor, put it on the well, drop the suction pressure from 125 pounds down to 5 or 6 pounds. And now the gas bubbles, instead of wanting to go up the pump, they're more likely to be drawn up in the casing. So now we have the same picture, but now because we've changed the pressure in the casing, the bubbles are now wanting to rise up, and they don't want to necessarily go into the Mother Hubbard or whatever separator you might have, and you get a much lower bottom hole pressure. Now if you have, let's say you had bottom hole pressure of 400 pounds and you had casing pressure of 60 pounds. If you take that 60 pounds of casing pressure off, then your bottom hole pressure is going to change to about 240 pounds. So now if your kind of formation is susceptible, most formations I look at them as either Swiss cheese or cheddar cheese. If it's porous and you have the ability for the pressure drop from near wellbore to go through the formation, it's a Swiss cheese. So you can get that pressure drop to communicate farther away from the wellbore. If it's cheddar cheese, you're just going to get a pressure drop right around the wellbore, and you're really not going to get much oil out. That's Lance has cheddar cheese.
One of the wells didn't have any pressure, and it shut in. So.
Yeah, well, this has always been my theory, and a couple people are starting to believe me. Is that, I was just in a meeting or a presentation, the guy I was talking about, the velocity of gas is 6 feet per second or whatever, and that's probably true. But if you're going into, instead of no longer having 60 pounds of casing pressure, you have 0, the gas bubbles in that casing are going to do the exact same thing that they're going to do in the beer that you open the top off of. When you take a bottle of whatever fluid you're drinking, there's gas in the fluid. But because you have a top on it, the casing pressure, the pressure above the fluid is constant. Because on your wells, you have a check valve that keeps the casing pressure pretty constant. So as soon as you take the top off of the beer, the bubbles want to do what? Go up, get out of there. So they'll create foam, which is what happens in horizontal wells quite often. We'll talk about in a second. But what you'll see is that the bubbles that were in the fluid have now expanded and are rising at a very much faster rate than what they were doing before. And this is the different rules and laws that we've sort of seen, but that's sort of what happens when you get rid of casing pressure. The gas bubbles are going to rise faster. And if they're rising faster than the fluid's falling into a separator, you should get much better separation. So on horizontal wells, most people consider horizontal wells foam generators, and they always blame it on the fluid. Well, it's not really necessarily the fluid. You have all of this gas is rushing through all of this fluid, and that's just what's going to happen. You're going to create foam. Everybody's used to, in vertical wells, you just didn't have that much pay zone where there was that much gas that was going to flow up. Maybe your pay zone was 300 feet. Perforations came out, gas came out. There just wasn't that much fluid. But now you got gas that's a half mile way back over there, and it's just traveling at, let's say, 7 seconds of feet a second, and it's just traveling through fluid. You know, and oil has a nature, if it's got some paraffin, it has a nature to foam. So it just has that little gas bubble is going to go from a mile at the toe of that well, and it's going to travel up the surface, and it's going fast, and it's going to create foam. So what happens on a horizontal well, when we take that casing pressure off, we entice that little gas bubble to move faster and get bigger. And when it comes to surface, it usually has, since it's a bubble is made up of gas and liquid. It now brings liquid to the surface as we start flowing fluid up the casing, and we start flumping the well. So when we install a beam gas compressor on a horizontal well, as we do up in North Dakota, you know, bunches of places, we normally will put some kind of a vessel between the wellhead and the beam gas compressor. That's so when this fluid starts coming up the casing, we can capture it, because I can't have it go into my beam gas compressor, because the beam gas compressor is completely under control of that walking beam. You know, that walking beam will not stop regardless of what my operation is doing. So we'll put a vessel in there so we can dry out the gas. Now, the compressor itself can handle high BTU gas, but the one thing that we can't handle is a slug of fluid that comes up with that. And I talk to many people, and they go, you know, you have an 8,000 foot deep well. You take 60 pounds of casing pressure off, you're not going to carry fluid up to the surface. And I'll say, well, you're wrong, because we do it all the time. And it's got nothing to do with the casing pressure. It's got to do with the velocity of the gas. Because if you have gas moving at a fast velocity, it will carry fluid. I mean, that's what gas lift is all about. You know, and when you have zero pressure for 3,000 or 4,000 feet, you know, and you have gas that's out here, it's seeking, it's wanting to hit an area of low pressure. So it's going to rush towards that area. And then more often than not, typically horizontal wells are all known having high fluid levels in the annuals, because you can't pump them because of the gas interference. You know, I mean, so you get fluid coming up. So the thing, this is just the schematic for putting the there. So this is a horizontal well. Now we have in this picture is an Odessa gas separator in the well, and they are trying to pump this well so that they get more fluid. But what happens is the gas comes up, and they've got casing pressure of 150 pounds. You know, it's sort of like that same bottle of beer. You know, the gas is there in the fluid, and it wants to go somewhere, but there's really nowhere for it to go except for up the pump. And so every time that pump strokes, it creates a void of fluid. Now, you assume, and I don't have my pointer, you know, where those little green parts are going in, you know, all of this, all the way down to the pump, that's all full of fluid. So as soon as this pump strokes up, it gets rid of the fluid that's right below it. And as soon as it gets rid of the fluid right below it, what happens to the fluid above it in that separator? Well, now it falls down. Now, so all the fluid falls down, but right around that port where you create a void of space, and now the gas goes, hey, I can go in there. So the gas goes in there, gets covered by fluid, and you start getting more gas in your separator. And more gas goes up in your pump. You know, something that happens. But if we go and lower the casing pressure, now we give the gas a choice that we can now draw the gas up to surface. And so now when your plunger goes up in your pump and you lose fluid in the separator, that hole right by the input, the gas is going to have a choice. Do I want to go to zero pressure in the casing, or do I want to follow this fluid? 60% of the time, the gas is going to go to surface. You're still going to have some gas will stay entrained in the fluid. But just like that bottle of beer, when you take the top off, you just let that sit there, and after a few minutes, you're still seeing bubbles going out of the fluid all on its own because it's seeking lowest pressure. So the problem we run into is that as soon as we start doing all of that, I'm going to start bringing a lot of fluid to surface. One of the first places we just sort of did this was out in California. Have anybody worked in California? They got a lot of rules. And we were doing this on a steam flood for Chevron. Now, a steam flood, by its nature, has dead oil because there's no gas to drive it. And so even when you have a well that has hardly any gas, you still develop pressure. So the less pressure you have, lower bottom pressure you should always get. So on a steam flood, what they would do is they would, if you have the well bore, they would inject 1,500 pounds of steam at 500 degrees Fahrenheit into the well bore, and it would go into the formation. They would let it sit there for 3 days. After 3 days, they would open the valves and they would take that gas pressure back out, all but about 100 pounds. So here they've added 100 pounds of casing pressure to their well because they were thinking they were trying to get the gas to loosen up so they could pump it. So we came along, well, we'll go ahead and take that casing pressure off. We'll take that steam off. And so we take the steam off, and now we start making 30, 40 more barrels of oil a day on their wells. But what also comes up with it is fluid. So we tell Chevron, okay, you can spend $25,000 on this beam compressor, but you're also going to have to put a vessel with a pump to take care of this fluid. So the facilities guys start going, well, the pump has got to be rated for 1,500 pounds of pressure and 500 degrees Fahrenheit, and it's a 1/2 horsepower pump. So the cost of the pump was more than my compressor. And it just seemed like it wasn't a workable deal. So that's where we started thinking about, well, how we can make a compressor that can handle multi-phases, where that we can handle gas, water, and fluid all in the same compressor. Well, the first problem we have is that we cannot be tied to a pumping unit, because if we're tied to a pumping unit, the pumping unit's in charge of going up and down. We want to be in charge of going up and down. What we did was we started looking at different methods. Now this is a screw compressor, and one of my favorite words in the world is simple, because I am. And this screw compressor is pretty complicated. There's a bunch of stuff involved in it. And the main reason there's a bunch of stuff involved in it is because they've got a separator that they've got to pull fluid off, because their compressor can handle fluid. Now this is our compressor, and you can see all the pieces that we no longer require. And that's because we're not concerned about having dry gas going to our separator, our compressor. We're not concerned about having a scrubber. And if we don't need to have a scrubber, I don't need to have a 1/2 horsepower pump taking the fluid out of the scrubber, and I don't have to worry about the compressor shutting down because it's got fluid in the scrubber. I can just continue doing it. So what we did, on the beam gas compressor, we had a pumping unit with a piston, and the piston was attached to the walking beam. And so here we elongate out the piston rod, and we add another piston to the top, and we put a hydraulic cylinder at the top of that. So now what we do is take a motor and a hydraulic pump, and we pump fluid into the hydraulic side, and it drives the piston up and down. And as that top piston is going up and down, guess what happens to the bottom piston? It now goes up and down. So now we can suck gas and discharge gas because we're driven by a hydraulic means. If we get any fluid into our gas chamber and the piston comes down and hits the fluid, our system just considers that all hydraulic pressure. And we design it so that it can continue pushing down, because now we're in complete control of the piston rod. So I can tell that piston rod to go down as fast or slow as I want to. And if I'm going into fluid, normally we would design having maybe 1,000 pounds of hydraulic pressure. So if I start getting fluid in the bottom side, I might now have 1,200 or 1,300 pounds of pressure, hydraulic pressure, which is what it's needing to push the fluid out. Fine. Once we get to 1,400 pounds of pressure, we just tell it turn around and change direction and short stroke until we get rid of all the fluid. So it's a pretty simple concept. Here you have the compressor. Once again, it's very, very simple. The most important aspect of this is you got 4 check valves that allow the gas to go in and out of the gas compressor. And then you have another directional valve up at the top left, which is really the heart of any hydraulic system. Because you have a hydraulic pump that's pushing fluid, and the directional valve either goes left or right, and that tells the fluid either to go into the top or bottom of the hydraulic chamber, which makes the piston go either up or down. It's pretty simple. It's not very hard to figure out. So now, when we get up to the top, we have sensors in there that say, okay, the piston's reached the top of the stroke, let's change direction. Directional valve just takes a signal from the PLC, changes direction. No big thing. One of the things I like is the compressor is dual acting, just the same as our beam gas compressors. And here you'll see one of our first units that has been sitting out in Loco Hills for, I guess, 6 years now. We just took a barrel of water and we're just sucking water, and it just discharges. Doesn't change anything as far as the functionality of our compressor. But that's the reason why we don't need to have a scrubber on the system. It's because if it's gas or oil or water, we can easily just move it out. And depending upon the size of the system, we can move the fluid. And this is the same young man doing. It's just real simple. Most skid compressors operate 95% of the time. The reason why they don't operate the other 5% is because of downtime for maintenance. We run 99.8% of the year. And usually the reason why we go down has got nothing to do with us. It's something to do with automation or something. It's just a series of check valves and transmitters. Our systems, we also do not provide automation. We're not an automation company. You guys have automation people. You guys have automation systems. We simply make our system work with what you're used to. That way there's no learning curve involved. Makes it, once again, simple. This is the basic layout of the compressor. You have a hydraulic motor, hydraulic pump, and a motor. It can be either electric or gas, or we're getting ready to start doing air driven for offshore oil rigs. That's why we'll be at OTC next week. This was a chart that one of our clients did. They were comparing long-term maintenance costs on our units versus the other guys. The first couple of lines for the first year is really just the purchase value of the equipment. But in these systems are designed to last for 10 years. And at the end of 5 years, we're almost half of the maintenance of other people. And I don't think and this is a cumulative cost, okay? This is not yearly cost. So, whereas the other guys almost doubled their original purchase price. Our cost has gone up maybe $30,000 or over 5 years of maintenance on a system that originally cost $150,000. This is the basic piping and instrumentation drawing. This is a pretty complicated system for us because this is moving 300 MCF of gas from 0 to 100. It was designed for a relatively large customer here in the basin. But it's just pretty simple. You know, if you know anything about hydraulics, it's just oil flowing back and forth and left and right. Advantages over screw packages and other types of separators. To me, the biggest one is variable frequency drive. We don't require one. We have the ability by using a proportional valve that handles our fluid. It can see the amount of suction pressure, and depending upon the control system, it can go faster and slower based upon the pressure and how quickly do we want to go down or go fast. And that all is about how much fluid goes through the directional valve. With hydraulic systems, they don't really do anything with pressure. All they are is about fluid, or volume of fluid. The more fluid that you flow, the faster our system will go. So a directional valve, if it's 1/3 open, we may be flowing 60 gallons per minute. And at 60 gallons per minute, we're going at 4 cycles a minute. The directional valve opens more, and we're now flowing at 100 gallons per minute, and now we're going at 7 cycles a minute. So the faster we go, the quicker that we can lower casing pressure, or if more volume came to the tank. You know, so VFDs are normally a pretty complicated. It's another thing that requires automation, some other technician, some other person to be out there. Proportional valve is just the same as a, what's the name on a light switch when you just turn it, you get more light or less light? Somebody.
Dimmer switch.
Yeah, it's just like a dimmer switch, proportional valve. You know, so it's pretty simple. These are some examples of different sizes, you know, because our compressors, we base them out of how much discharge pressure we need to have and how much suction pressure we're going for and how much volume, and then we can come up and something for you. These are some different places that we've got these installed. This is in New Mexico. This is out in Loco Hills. It rained out there. So, I mean, I'm just saying, because if you've been to Loco Hills, you know, it doesn't happen all that often. But we were there the day after it rained. So this is another one. Another one. You know, these are, you know, all of them in Loco Hills. This one is in a city of Odessa. Has 16% H2S. I don't know if you guys really get around H2S that much, you know, but our systems are designed where we can go up to 20-25% H2S. How many are familiar with NACE? NACE is all about a requirement to be able to be corrosion resistant against CO2, H2S. All of our systems are basically NACE compliant. That's just the way we make them. It's just by design. You know, we don't have to do a whole lot to make it NACE compliant. It's already pretty NACE compliant. There's not a whole lot that's left other than changing a pressure release valve. That would probably be the only thing we normally.
What were they doing with that gas when that was so warm?
Well, that was as a vapor recovery. They were just taking it and putting it back into the cell line and pushing it to the battery because it had, you know, it was like 15 MCF gas, you know. But I'll tell you where it is. I won't do it. I'm recording, so I won't. But it was in the city limits of Odessa. This is one that we sent up to North Dakota. And remember I said this is simple. Well, we built this in Odessa, Texas. We put 5 different places for them to plug their transmitters to. I sent them a basic program for their Allen Bradley system. We shipped it to them. They set it. They plugged in their transmitters. They turned on their Allen Bradley, and it worked. And I haven't seen it since. And that was back in 2015. You know, we haven't had to do anything to it. And that's, you know, coming on 2.5 years now. You know, but you know, you couldn't say that about virtually any other kind of brand of VRU or other, you know, you got to have some specialist, you know, And specialists aren't simple. They're educated. They went to school. This is one of our larger systems at doing 300 MCF of gas. One of the things we was that we have a job in Columbia that we're going to do where they were going to originally buy a $5 million compressor to handle a large amount of gas. Now, if you buy a $5 million compressor, well, that sucker is going to have to be maintained. And what's going to happen to your production when you're maintaining that compressor? Your production is going to go down because your pressure's gone up. That's why you got the compressor in there. So we designed where that we would put 20 of our units side by side, and they'd run 19 at a time. So at any given time that they wanted to maintain something, they just take one off and turn one on. And so they had 100% runtime. So not only were they running it 100% of the time, they didn't have lost production. Now, if you lose 1,000 barrels of oil a day for 3 days, 6 times a year, that adds up. This is a unit for a Chevron out in all right, does anybody recognize the area? There you go. You know, and this is that one we were doing with steam floods, you know, where they would set this on in a location where they could plumb multiple different wells to it. I just always think it's a neat picture. And I've never had people not know where it is. Maybe occasionally they'll say Local Hills, because that's the only other place I can even think that's close to. You know, but one of the big differences between our compressors and others is that, you know, how many have ever heard of the term blow-by? Well, blow-by is when the piston of a compressor pushes this way and the gas, as it's being compressed, blows past the seal of the piston and goes to atmosphere. It's one of those things the EPA likes to take a flare gun and shoot your compressors to see the gas that's coming out. Well, in our system, because of the triple redundancy in the head, you know, the hydraulic cylinder is always going to have more pressure than our seal between the hydraulic and the gas. So the hydraulic pressure is always going to keep the seal closed, so there's no way that the gas pressure can ever get past it to get to atmosphere. So we don't have any blow-by past our piston, because our piston is inside 2 different chambers that are just compressing gas. So that's an interesting thing the EPA likes about it, you know, simply because we can eliminate emissions. The reason why we're doing it on offshore platforms is, once again, we don't have any emissions. You know, even though the amount of emissions that they might have in blow-by is minor, you know, whenever the government wants to shut you down, they can figure out any little reason they want to and say, hey, you know, that's bad, so we're just there. On this particular installation, those 2 panels are the Allen Bradleys that the customer wanted. Nowadays, we've gotten so good at it, or the customers have gotten so good at it, usually on a battery, you already have some kind of automation. All we need are 5 inputs into the existing automation you have. We don't need a whole new system. On a wellhead system, we can actually go right into your POC. And this is what we were designing with Chevron, was to go into their existing SAM units, you know, because they would just add another card. You know, so this system is very simple. I said that before, but it's very simple. It doesn't require a lot of technology to make it work. You know, so the less technology, the less bells and whistles on the system, the less that you have that's going to go wrong. This is that same picture in California where they had the different locations looked out. This is the big area, I think, when we get into horizontal wells, is on ESPs. You know, when you design an ESP, one of the factors you put in there is how much inefficiency is the ESP going to have? How much gas interference is that ESP going to see? And you have to design it to be at 85–90%. But if you pull the casing pressure off and you redesign your ESP with low casing pressure, well, then you get to the point, well, there's more fluid. You know, now you're running at 95, you know, much more greater efficiency. But the same example that happens when I pull fluid up on a horizontal well, I'm going to do the same thing on a horizontal ESP well. So by having a compressor that can handle the fluid, it eliminates the downtime. You know, because if you have a compressor that's taking 150 pounds of casing pressure off of an annulus of an ESP, and the ESP gets to where it likes that, then all of a sudden the fluid flows up and it gets into the scrubber system of this compressor, and the compressor shuts down because it needs some guy to come out there and empty the scrubber. Now the ESP is now running at full pressure on the casing. It won't like that. You know, because now it's being run with something it wasn't designed for. Because now all that gas, a lot of it's going to start going up in the ESP. So, you know, hydraulics, beam gas compressor has been around for 40 years. Hydraulics have been around for hundreds. You know, they're very simple systems that have just a lot of history of going out there, and we just put the two together. You know, so in summary, basically it's variable frequency drive, and the proportionality is good. Another one that I like is that we don't have to cool the gas. You know, one of the systems we went on was for a well in Andrews, and they had a compressor where the compressor would send hot gas down the sales line, because in a compressor itself, it's going to only run at 3 or 4 or 5 ratios of compression. You know, so that gas is going to get hot as soon as it gets compressed, and then it's going to go in that sales line, and as soon as it hits the sales line, it's going to cool off as it goes down that sales line. And if the gas has a high BTU content, what's going to happen is that liquid's going to drop out in that line, and you're now pushing liquid at your gas company. And they don't like that. But with our system, because we run at 9 ratios of compression, we don't heat the gas up, because another compressor system is running at 1500 RPM. I'm running at 9 RPM. I'm going up and down 9 times a minute. I'm going very slowly, as opposed to 1500. So that's another big issue. That thing that we allow is that we don't heat up the gas, so that when we do compress the gas, we do put it down the sales line, there's no liquids that are going to drop out. You're just going to be sending gas with a high BTU content down to your gas company. Answers? Okay, I got questions. No. Any questions? Mr. Chairman? Well, I appreciate you guys coming.